Okay, so here we are ready for the chain rule, which is where we left off last time. So we went through quite a few different rules. In fact, I think we went through every one of them except possibly for the chain rule way back. We had a list here. Let me just go open it back up again. Here we go. The constant rule, the power rule, rules for sums and differences, the product and quotient rules, the generalized power rule, and then finally the chain rule. So this, we've saved this one for last. We're going to see a lot of it, though. It's a very important result. And so it's an important to be able to recognize cases where you need to use it. And so keep in mind that the chain rule is based on cases where we actually have a composite function. So we have to treat it very carefully. So how does this work? Okay, so first of all, what we're going to do is rewrite our problem a little bit. This notation is a little bit different than what we've been seeing. You'll recall from way back in the beginning of the course, we saw that, or at least the beginning of this chapter, the first derivative can be written in a few different ways. And so we haven't really been using the dy dx notation, but sometimes it does come in handy. It's, the notation can be useful for many different applications. Sometimes you'll see when we get to, for example, something called implicit differentiation later in this chapter, the prime notation will actually prove to be very helpful. When you're evaluating functions, this is probably the best way to go. But for something like using the chain rule, then the dy dx notation can actually be very useful because you can see visually what you're doing, and you can see that we're treating y as a function of u, and then u in turn is a function of g. So in other words, we have a composite function, f of g of x, but f itself is a function of u, and u itself is a function of is itself g of x, a function of x. So what we've done is we've taken a composite function and written it in a slightly different way. And the reason for doing this is so that we can rewrite our dy dx as dy du times du dx. Now you might think, well, why are we making it unnecessarily complicated? Well, no, we're not actually making it unnecessarily complicated. As you'll see, this is an easier way of approaching the chain rule than maybe some of the other approaches you might see, maybe in the book or in another book. So, and here's again, remember, I think I mentioned this discussion about the history of calculus being traced back to Sir Isaac Newton and Gottfried Leibniz in Germany. And they both were very jealous of their role as the creator of calculus. But historians pretty much have agreed that Newton probably got there first, but Gottfried Leibniz, independently, without realizing what was happening in England, also at the same time roughly developed calculus as well. So a lot of the notation that we see in calculus came from either one or the other of these two. Anyway, so let's start with a simple example. So f of x is this entire expression, f of 5x cubed minus 2x squared plus 3. Now the entire expression is raised to the fifth power. So we don't want to do this ourselves. We don't want to multiply this by itself 5 times. We'd have a polynomial that's longer than this computer screen. If we did that, of course, we could go ahead and use the rules that we know and come up with the correct derivative, but it's not necessary because the chain rule will make it a lot simpler for us. So here's the way we have to approach it. So remember, we did say that y is a function of u, and u is a function of x. So what we're going to do is this. We're going to designate this expression as u. Now, when we're doing this approach, it's not always obvious which part of this function should be designated u. That takes a little practice. But when we have a polynomial like this raised to a power, usually it's the polynomial that becomes u. And the reason why we're doing this is because we can then simplify and write y is u to the fifth power. So how does that help? Well, remember, we did say that the chain rule can be written in the following way. Okay, f prime of x is dy dx, or in turn dy du dx. So if u is, actually, let me just copy this. Here's our u. Oh, what happened there? Sorry. Okay, so u, this, no, there's not this part. U is everything that was inside the parentheses. And y is u to the fifth. Okay. So if that's the case, then we know two things. Starting here, dy du, the derivative of y with respect to u is, using the power rule, 5u to the fourth. So remember how that works. Or actually, what I should do here to be consistent is write this as dy dx. Okay, so for dy dx, derivative based on the power rule, this would be nk x to the n minus 1. So the fact that we're letting the independent variable be u is not really relevant. The power rule still works here. So by letting y equal 5u to the fourth, dy du, based on the power rule, is 4 times 5. Whoops, sorry. Whoop, let's look at the wrong thing. Hold on. U to the fifth. Okay, that's better. 5 times u to the 5 minus 1, which is 5u to the fourth. That's where this is coming from. So in other words, we applied the power rule to y equals u to the fifth power. And then in turn, du dx, remember, u was defined up here as a function of x. So we're going to apply the power rule to each term individually. Okay. And so we end up with 15x squared minus 4x. Now this just goes to 0. We don't normally write it there, but there's implicitly a 0. And so we end up with du dx is 15x squared minus 4x using the power rule or applying it to both terms. Actually, all three terms, but the third one drops out. So we have dy du, we have du dx. So now it's just a matter of substituting what we have into this expression. All right, so remember, we already determined that dy du is this term, and then this is du dx. Now, there's just one more step. We don't want this u in here. We want an answer that's in terms of x, but we've already defined u to be here. Okay, let me put this up here to remember, so we can remember. And so what that means then, as you'll see in the next slide, is we're going to replace this u with what we have here. Okay. So therefore, this is what we have. Instead of 5u to the fourth, we have this. Okay. So in other words, remember 5x cubed minus 2x squared plus 3 is u. Therefore, this is what we get when we replace u with the function of x. And so this is actually our final result. This, what you're seeing right here, is the derivative of y with respect to x, or f prime of x. So I think you'll agree. Now, once you get the hang of this, you'll agree that this is a lot quicker than trying to expand this. Imagine how long that would take to multiply this by itself 5 times. The number of terms would be out to here. This way, it really only takes a couple of steps. And this is our final answer. Now, if for some reason you really need, you can certainly raise this part to the fourth power. And again, it would take a long time, but this is fine. This is the way you would normally leave this, unless there's a good reason to expand it further. Okay, so this is a classic example of the chain rule. So the challenge here is to look at this expression, first recognize that we should be using the chain rule, and second, trying to determine which of all these terms in here should be represented by u. Now, suppose you guess wrong and you pick the wrong thing for u, you would discover pretty quickly that everything is getting messier rather than simpler. And that would mean you go back to the beginning and say, well, let me try something different. Okay, because like I said, it's not always immediately obvious what should be defined as u when we're using the chain rule. If you do it correctly, you'll get your answer very quickly. If you've done something wrong, you'll discover that you're just making a bigger mess. Okay, so this does take a little practice. All right, let's look, oh boy, trig functions. All right. By the way, I'm going to make a note to myself. What I usually do at this point in the course, when we're just about done with chapter 2, what I like to do is just bring out a bunch of examples and just run through them all. I think we're just about there. I'm going to make a note to myself that maybe our next section, our next session, I should say, should be that session where we do a lot of practicing. Okay, I think we're getting to that point where we know enough rules that we could benefit from a bunch of practicing. So I'll make a little note to myself. And that way we can run through all the rules and practice them with more examples, because this is the type of material that the only way to learn it is to practice. Okay. If we were in a regular classroom setting, we'd be spending a fair amount of time doing that anyway. So, and we're ahead of schedule as it is. So, it won't do any harm to spend at least one session just going through and practicing. As a matter of fact, while we're in the subject, I'll tell you what we can do here. We can do another of these just to see how it works out. Okay, just to see one more example of this approach when we're dealing with polynomials. So let's just say that we have y equals okay, here we go. Here's an example. Now, you can see that you've got a polynomial raised to some exponent. That's usually a hint that you probably should use the chain rule for this type of problem. So how do we do that? All right, well, remember the way this works. So let's choose a u, okay? And in this case, let's choose this expression, this is u, so that y is now u to the third power. Okay, so how do we find the derivative? Well, before you do anything else, what you want to do is figure out the values of dy du and du dx. Okay, so dy du is very straightforward. So if you think of this as k x to the n power, k is 1, n is 3, except that the independent variable is u instead of x. Okay, so you end up with n k x to the n minus 1, which means 3 times 1 times x to the 3 minus 1. And since we're dealing with, or u is the independent variable, we can rewrite this as 3u squared. Okay, so based on the power rule. Then we need du dx. And here you've got two terms, both of which can have the power rule applied to them. So since u equals 2x to the fourth minus 7x squared, if you apply the power rule here, in this first case, of course, here's k, here's n, here's k, here's n. Don't forget this is negative. So you'll have 4 times 2, x to the 4 minus 1. Over here, you'll have minus 2 times 7, x to the 2 minus 1. And that ultimately gives us 8x cubed minus 14x. Great. So now all we have to do is substitute. And well, actually, we're substituting twice. Okay, you'll see what I mean in a second. Because we need both dy du and du dx. We just got through showing that dy du is 3u squared. Du dx was 8x cubed minus 14x. But we also remember that u was defined in the first place as 2x to the 4th minus 7x squared. So finally, our ultimate final result is 3 times 2x to the 4th minus 7x squared, to the whole thing squared, because remember, it's 3u squared. And then we have du dx, which is 8x cubed minus 14x. Oof, it's a long, messy expression, but again, it's quicker, a lot quicker than expanding the whole thing and trying to apply the power rule to every single term, because there could be dozens of terms by the time we're done. So I think you'll agree this is a lot quicker. Okay. Okay. So anytime we have a polynomial raised to an exponent like this, we're going to take the same approach. But sometimes we don't get that lucky. What happens if we end up with a trig function? Oh boy. Okay. So now it's going to be tricky to decide what to do about u, because there's a few different things we could do. So what we're going to do here is try this. And by the way, as far as the notation goes with trig functions, the convention is to put sine cubed x like this, but all that really means is the entire expression is being cubed. So if that's the case, why don't we try this? Let's let u be the sine x. Okay. Well, if that's the case, then our function could be thought of as u to the 3rd power. Okay, fine. So remember again, if that's the case, so remember we need, as far as this definition is concerned, we need dy du, we need du dx. Okay, so here we see that applying the power rule leaves us with 3u squared. And over here, you'll recall, remember we went through this a while back, the derivative of the sine of x is the cosine of x. So when you plug these in, you're going to get 3u squared cosine x. But remember, u itself is the sine. So this is our u squared. So we end up with 3 sine squared x cosine x. So yeah, like I said, these do require a fair amount of practice, especially something like this. Now, like I said, if you tried something else, let's say you decided to try sine squared of x for u. Again, you would have started to work on it. You would have discovered that you're making the entire thing messier than it started out. And that would be a hint that maybe you should try something different. Okay. Because sometimes, like I said, you're maybe not guessing, but you've got a few options to choose from. And just use the one that simplifies everything. Wow. Oh, by the way, in case I found this chart, this very helpful chart. If you are not sure These are the trig derivatives, except this time, if you notice, it's not sine x, cosine x, etc. It's sine of g of x, cosine g of x, etc. So in other words, these require us to use the chain rule. And this is the result on the right-hand side. Okay. So what we just did here, well, that wouldn't be listed here separately, but the derivative of the sine of u is the cosine of u times du dx. Okay, and so here's the entire set that you might need if you run into these. Okay, now it turns out that we can also take derivatives of inverse functions. Wow, this is really getting intense, but the point of what we're about to do is to make it simpler for us to solve for these very complicated derivatives. So if y is the inverse, or sorry, if f inverse of x is the inverse of f of x, the derivative of that inverse is 1 over the derivative of f inverse of x. In other words, what you're doing here is you're evaluating the first derivative with the inverse function itself. Now that sounds like a nightmare, but why don't we try this? And if this is confusing, what you can do is just think of g of x as the inverse, and then maybe this one looks a little cleaner. So you notice what's happening down here. We are taking the derivative of a composite function, which means that we're using the chain rule. Wow. All right, well, let's try something like this. Now, in fact, while we're at it, why don't we review how to find an inverse? Okay, here I'm just telling you what it is, but just in case, I mean, I know we mentioned this when we were doing our reviews in the beginning of the course, but I'd like to go through it one more time. So let's say we have, we know that f of x equals 2 over x minus 1. So let's write it as y. It's just a little bit easier that way. So what you're doing is you're reverse the x's and y's, and then solve for y. Okay, so here that means this becomes x equals 2 over y minus 1. So we'll move that to the next slide. And then we multiply both sides by y minus 1. And we rewrite this as xy. I'm distributing the x over y minus 1. I add x to both sides, divide out the x on both sides, and this is the inverse. Okay, so the original function was 2 over x minus 1. The new function, the inverse, is 2 plus x over x. All right, now, like I said, it tells you here, but I want to make sure that we don't forget how to do this ourselves. Okay, it's a very useful skill to have. All right. So this is the formal rule, the inverse theorem rule, inverse function theorem. A theorem, the way it works in the hierarchy of math, theorems are pretty high on top. When something is called a theorem, that is extremely important, to say the least. Yeah, these sometimes you find results that have names like lemmas and things like that. No, this is serious business. It's a theorem is a very important result in math, and so what we're going to do is use that theorem to say, well, if that's the case, what's the derivative of this inverse? Now we can do it ourselves with the quotient rule, but for this one, we'd like to try the inverse theorem just to see how it works. So given that f of x is 2 over x minus 1 and g of x In fact, I'll tell you what, why don't we double check this with the quotient rule? Is 2 plus x over x. So we want to know what is g prime of x. Okay, which this notation is the same thing as g prime of x, by the way, just to make it clear. Okay, so it's telling us to take f prime of g of x. So what is f prime? Now, here, this is f prime. This means this is f prime of x being evaluated where x equals g of x. So we have to take the derivative of f of x. And that means we have to use the quotient rule. Okay, so remember how that works. If you assume that f of x is g of x over h of x, then f prime of x is no, sorry, my mistake. There we go. Okay, so the original function was 2 over x minus 1. So using this notation up here, that means that g of x is 2. Let's move this aside for now. So that means that g of x is 2. And you'll recall that the derivative of a constant is always 0. Based on the power rule, we can prove that because g of x is a constant, its derivative is just 0. Now here, so when we take the derivative of x minus 1, we're basically applying the power rule to both terms. And you might also recall that we said that if you have a function like just kx, its derivative is just k. So these are two special cases. The derivative of a constant is 0. The derivative of a constant times x is just k. So that means h prime of x here is just 1. So when I plug that into this really messy formula, I'm going to get x minus 1 times 0 minus 2, 1 all over x minus 1 squared, and I end up with minus 2 over x minus 1 squared. Okay, so what comes next? That's f prime of x, but we need f prime of g of x. So we take this expression and we replace the x's with g of x's, as you see right here. So let me copy this to the next slide. And so to get to f prime of g of x, we're going to wind up with x becomes g of x. And we already know that g of x, the inverse, is 2 plus x over x, or x plus 2 over x, as you can see. So this is actually the final result. We can expand on it if we need to. And it looks like I did it, go ahead and expand on it. But you could actually just leave it like this. What I basically did was I combined the two terms in the denominator with a common denominator, and then you can see that you've got 2 over x, entire expression is squared, minus 2 over 4 over x squared. Remember how this works. When you divide by a ratio, you're multiplying by the inverse. So it ultimately ends up as minus 2 over x squared. Let's see. Oh, yes, because I'll tell you what, yeah, I was looking at it for a second, like what's going on here. I just realized this is your denominator. So we go back to the previous slide. We're trying to solve for this. So we just determined by doing some consolidation of these terms, the denominator of this derivative is negative x squared over 2. The numerator, oh, there's a typo here, isn't there? Well, actually, no, there isn't. It's 1 over. Sorry, I thought there was a typo for a second. So yes, anyway, we had to have 1 over the negative x squared over 2. And then just by rearranging that, and then we have our answer. Wow. So that was tricky because just keep in mind, this whole piece is simply the denominator of the expression on the previous slide, right here. All right. So now that's oh, by the way, why don't we do I mean, if you want, maybe we don't need to do that right now, but you could actually go back and say, well, listen, what if I simply want to do this with the quotient rule? You could certainly apply it and you'd see that you get the same thing. Okay. All right. Anyway, now that was 2A. 2B, we're going to do a few more interesting things here. So first, this is, of course, a review of the power rule. We've seen it many, many times. What we want to know is what happens if n is not an integer? Can we still apply this rule? Well, we're going to see what happens when the exponent here is what we call a rational exponent, meaning a ratio of 2 integers. So in other words, imagine you have something like this. We have, so this could be, for example, 1 over x. Let's say we had f of x is x to the 1 over 2. This is the same thing as radical x. So the power rule hasn't actually changed. What's happening though is that you're multiplying. So it's almost like, imagine if I rewrote this. Then the power rule would be 1 over n k x to the 1 over n minus 1. Okay. Now, of course, if you want to consolidate 1 over n minus 1, what you can do is rewrite it as negative, or subtract n over n instead of 1, and you'll end up with 1 minus n over n. It's a little simpler. So this is, oh, well, all right. You can leave it like this, but if you want to, you can write it like this. It's a little messier, but it's still the power rule. Nothing's changed. Now, if we started out not with 1 over n, but m over n, based on the same reasoning, this is our final result. M over n times x to the m minus over n minus 1. But you don't have to treat this as a separate rule. I mean, it's the same exact setup. It's just that now you're dealing with fractions instead of integers. So let's say we had something like this. F of x is x to the 2/3 power. So here's our rule. And that means then that m is 2 and n is 3. So according to the rule, we're going to have 2/3 x to the 2/3 minus 1, which of course is just negative 1/3. So we're relieved to see that the power rule actually applies to cases where the exponent of x is not an integer. Now, of course, it won't work if we have something else like a sign or something. As long as it's a ratio of two integers, we can still use the power rule. Or how about this one? So again, let me copy the rule for you here. So here we can think of, since the exponent is -5/4, we can think of m as -5, n is 4. And so we end up with -5/4. And the exponent is -5/4, again, -1. And that can be reduced to -9/4. So this is our final result. Okay, so we could do this with any number, it could be 2/3, it could be 5/4, it doesn't really matter. It always works this way. Now here we're getting a little fancy. We're not asking for the derivative, we're asking for the slope of the tangent line to the function f of x equals x to the 4/5 at x equals 6. Which means what we're being asked to do here is first solve for the derivative, and then we find the derivative when x equals 6. Okay, so it's sort of a roundabout way of saying evaluate f prime of 6. And this is a two-stage process. First, find the derivative using the rule that we just discovered. Okay, so we're starting to get pretty good at this. M is 4 and n is 5. So that leaves us with this result for the derivative. And now we want to know the slope at 6. So we substitute x for 6. And here we can either leave it as 4/5 times the 5th root of 6, because that's what this is, by the way. Okay, why is that? Because the negative tells me that this is a ratio, and the fact that it's a fraction tells me that it's the 5th root of x, okay? So if it had been x to the 1/5, we write that as the 5th root of x, but because it's -1/5, the exponent is -1/5, that means we're looking at 1 over the 5th root of x. So here we're doing that where x equals 6, and this turns out to be approximately 0.559. So just for the fun of it, why don't we take a look at this graph on Symbolab. It's kind of hard to visualize something like this. So let's do this. It's first, it's 4/5 x. Oh boy. Whenever you see blue there, you know it's going to erase everything you've done. X to the -1/5. Okay, well, that is a bizarre function. And then where x equals 6, right here, the slope of the tangent line is 0.559. That looks about right. It would be very flat right here. Certainly it's less than 1, but it's not 0. Of course, you had to know there's going to be an asymptote at x equals 0, because you actually, if you rewrite this as 4/5 of 1 over the 5th root of x, you'll see that we can't allow x to be equal to 0. All right. So I'll tell you what, let's just make up one more quick example. All right, what should we do? Hold on, I have lost my marker. Oh, no, here it is. All right, let's say this is our function. So now keep in mind the formula itself refers to the exponent, not the 3/8. That's just a constant. That's a coefficient. Okay. So in other words, here you've got this expression. In fact, actually, this is a good example because what it's telling us is that if this is your function, this is your derivative. Which implies that if f of x equals something like this, k x to the m over n, then the derivative is nothing but a times this whole expression. So that means here the m is -2, the n is 3, and the k is 3/8. So according to this formula, I'm going to end up with k. Here I'll have negative m over n. The exponent will be this. Okay, so it's a bit sloppy. It's messy, of course, but actually, let me copy this to the next slide. So now when you multiply 3/8 by -2/3, you get -6 over 24. Up here, you're going to need a common denominator. And 6 over 24 is just 1 over 4. So we'll rewrite this as -1/4 x to the minus 5/3. Okay. So the presence of a constant coefficient will not affect the rule itself, but it does mean we have to multiply that by our final answer. So that's why I've updated it here. I've extended it to include the possibility that there's some constant in front of x. And you can see all we had to do was hold that out in the outside, evaluate the derivative, and then whatever we get, we multiply by k. Okay, now inverse trig functions. What in the world is this all about? All right, so let's just give you a quick example. If you go to your calculator, by the way, this notation will give you a hint. These two are inverses of each other. Okay, f with that little -1, that tells me that this is some kind of an inverse. And so the fact that we're using a -1 here indicates that the arc sine, as it's called, is the inverse of the sine. In the sense that, all right, well, you'll see in a second what this is all about. So you go to your calculator and solve for the sine of 30. Unless you have them all memorized, you'll see that it's 0.5. Okay, by the way, you do see arc sine written as sine -1, but sometimes it's written out the words arc sine. This tells me that the arc sine of a half is 30. So think of the arc sine as saying what angle corresponds to a sine of 1/2. Okay, so we know that the sine of 30 is a half. This arc sine is basically saying what angle has a sine of 0.5. And the answer here is 30. Now, I'd, I'd love it if I could think of an example of this from some other application. Um, it's not coming to me. I'll come up with something. Like I'd like to have an example that you've seen in the real world. But no, 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 it's not happening. I'll try to think of something. But as long as you recognize that all you're trying to do is reverse the process. Instead of solving for the sine of an angle, you're solving for the angle of a given sine. And then we got the same thing for all the others. There's an arc cosine, there's an arc tangent. You know, we have one for all of them. So what this is showing you again is what I just showed you, that if you solve for the sine of theta, the arc sine of that value that you just came up with is the original angle. Okay. So yeah, here's the example we just had. Whoops. You might recall this symbol. I don't even know if it has a name. I tried to look it up once. I don't remember what I discovered. Degrees. Okay, so and you also recall just degrees can be broken down further. There are 60 minutes in a degree, and there are 60 seconds in each minute. In fact, you'll see this if you wanted to know, for example, the latitude of your position. Like we could look this up right now. Let's say, what is the latitude of New York City? And oh, for God's sakes, here it is. See there it is. So written in the style, it's not, you notice how it's not always written this way, but 40 degrees, 43 minutes and 50 seconds. Sorry, 50.1960 seconds north of the equator. Okay. So I just wanted to throw that out there. Just see if you remember that degrees themselves can be subdivided into minutes and seconds. Okay. Just in case. It's not going to show up in this class, but just in case. Um, Same thing here. The cosine of 90 is 0, which implies that the arc cosine of 0 is 90. The tangent of 45 is 1, which means the 45 degrees, that is 1, which implies that the arc tangent of 1 is 45 degrees. Now, as you can probably guess, what is this building up to? I don't even remember now if we mentioned this during our review, but the reason why it matters now is because, of course, as you can imagine, there are formulas rather that we can use to take derivatives of these inverse trig functions. Here they are. Now, oh my God, now these are getting a little complicated. And as you can probably imagine, if I replace that x with a g of x, then suddenly I need to use the chain rule. And I believe we have that chart here too somewhere. Oh, maybe not. We can find it. But this is, yeah, this is just for the inverse trig functions of x only. If we are applying this to a function of x, meaning g of x, then we need to use the chain rule. And what will happen is at the end of each of these, you would have g prime of x, whatever that is. Okay. But here are these, this is just x. Okay, so for example, what if we have this? F of x is the inverse, sorry, the arc cosecant. If you wanted to know the derivative, well, here it's just a simple matter of looking it up in your table. Okay, so our cosecant rather is the one on the bottom, -1 over absolute value of x times radical x squared minus 1. So for these, you can just look them up. Okay, here we go. So now, what happens when we do need the chain width? Okay, so uh, so yes, once again, like if this is g of x, we need, oh, and this becomes g of x too, of course. Yeah, it's a little sloppy here. I'll see if I can find a cleaner copy of this. Well, you get the idea. Okay. Here's an example. What if we have f of x is the arctangent of x squared? So let's go look it up here. 1 over 1 plus g of x squared. And then at the end, of course, we do need the g prime of x. So in this case, the g of x is right here. And once again, using our friend the power rule, here in this case, there's an implicit 1 here. So k is 1 and n is 2. So we're going to have 2, 2 times 1, I should put that here, x to the 2 minus 1, just 2x. Okay, so what we're going to do here is this. First, we'll simply plug in g of x, and then we'll plug in g prime of x. Okay, we know that the derivative of the arctangent based on our table is here. So that part is done. So really, it's just a simple matter of replacing g of x with x squared. Remember here, be careful here because it's x squared that's being squared. And then here, g prime of x we proved is equal to 2x. So in the denominator, you've actually got 1 plus x to the fourth, and then you can move this to the numerator, and you end up with 2x over 1 plus x to the fourth. Now look at this disaster. So once again, you can look up the formula for the derivative of the arc cosine. It's -1 over 1 minus g of x squared under the square root sign, that is. Here's g prime of x. So let this be g of x. And using the power rule on both of these terms, we'll end up with 6x plus 2. So now we're just going to replace g of x with all of this. And then this becomes our g prime of x. And that's our final answer. So remember, the g of x is 3x squared plus 2x. So this whole thing has to be squared. In the numerator, we have negative. Don't forget, the numerator is -1. So g prime of x, if I put this in the numerator, I'll have negative 6x plus 2. So with these, you have to be careful with all the negatives. That would be a real easy mistake to make. Oh, now look at this one. This one involves the product rule because you've got x squared times the arc sine of x. So you're going to have to use the product rule, and that means you'll also need to know the product. This would be your g of x and h of x. So you can use the rules that we've gone over to find g prime of x and h prime of x. And remember, this is the product rule right here. So if g of x is x squared, g prime of x from the power rule is 2x. H of x is the arc sine of x. And from our chart, we have now this is just x, by the way. We don't need the chain rule. It's just 1 over the square root of 1 minus x squared. So in other words, that one does not require the chain rule. So you can just use this one. And now you just plug them in. And there, realistically, there's no way we can simplify this. So you can just leave it like this. Okay, now what's coming up next is a very interesting application. It's called implicit differentiation. Now, what is this all about? What can happen sometimes is that you may have a function which is so messy that, normally what you do is you separate out all the variables. So you have something like this. You've got y on the left, f of x on the right, and you go ahead and apply the rules. But sometimes you may have a function which is so messy, like even this one, it doesn't look that bad, but how would you split out this y and move it over to the left with this y? Well, I mean, let's just say that it would be very messy. So in a case like that, it's not really worth your while to try to split it up like that. What we're going to do instead is use what we call implicit differentiation. What we've done up to this point was known we didn't actually mention this, but it was called explicit differentiation. Because y is an explicit function of x, but when it's not, like this, then we have to try something different. And this is going to take some getting used to. It's a little, well, all right. Well, you'll see what I mean when we get to it. So something like this definitely requires us to start in the beginning and just go through and work with it. It's not something you just mention in passing. Let's put it that way. So what I'd like to do here is put together some more examples of everything we've done up to this point for our next session. And if that takes up the whole session, that's fine. We could use the practice. But the next new topic we'll cover is this one right here, because it will take some getting used to. There's some concepts that we have to learn. Once you get the hang of it, it'll be fine, but it's different than what we're used to seeing. Okay, so we'll save that for the next time. Through practicing, we'll go through these and see how they work. Okay, I noticed in the assignments that there's an entire separate assignment for just this. Okay, so we'll get to that soon enough. So in the meantime, we'll stop right here, and then we'll pick it up next time with this so-called implicit differentiation. All right, see you then.